Now, the critical points are candidates for the local extreme values. We may not have a local maximum or local minimum. Instead, we may have something called a saddle point. A function f has a saddle point at a critical point if every open disk that's centered at AB has points for which the f of xy is bigger than that z value at AB, and it has points where the z value are smaller. So in other words, you'll have bigger, higher and lower points than that point, the z value at AB. So in other words, you can walk up the hill from there, or you could walk down the hill from there. Okay, so that's a saddle point, and you can see from the picture why it might be called a saddle point. Now, we had a similar behavior back in Calculus 1. If you remember the function y equal to x cubed. At this point at the origin, the derivative was 0, but there was neither a maximum or a minimum at that point. If you took an interval around x equal to 0, you had points that were higher than that, the y value here, and you had some points that were lower. So it's a very similar idea when you had a function with just one independent variable. Okay, so now the second derivative test. Suppose the second partial derivatives of f are continuous through an open disk centered at the point AB, where the derivative, the partial derivatives at AB are both 0. Now, we're going to form something called the discriminant. D of xy will be the second partial derivative, f sub xx times f sub yy minus f sub xy squared. So this discriminant is what we're going to use to determine whether a point has a local maximum, a local minimum point, a saddle point, or just that it's inconclusive. So determine that discriminant. Now, if the discriminant is positive, then we're going to have a local maximum or a local minimum value. But what determines whether it's a local maximum or minimum is the second derivative of the function f at that point. Now, if you remember, second derivatives measured concavity. So if we were looking at a second partial derivative, we would be looking at the second derivative then going in the x direction. A second derivative to be negative meant that the function was concave downward at that point. So what we have is in the x direction, we have that the function would be curved downward like this. So what happens when you have a point and the surface has that concavity downward in that x direction? Then what you've got is you've got a local maximum. Now, likewise, if the discriminant was positive and that second derivative was positive, well, again, in the x direction, the second derivative positive means that the curve in that direction would be concave upward. And when you have that situation, then at that point AB, you're going to have points higher than that. So that means that's going to be a local minimum. So this, think about concavity and what it means for a second derivative to be positive or negative. And just remember that this discriminant being positive is going to be what indicates that we will have a local maximum or a local minimum value. Now, if that discriminant, though, is negative, then f is going to have a saddle point. And if that discriminant is 0, then the test is inconclusive and we'll have to just look at the equation and try to analyze it. Okay, so now a positive discriminant, what that's really telling us is that the behavior in all the directions is the same. So, you know, it's either all going up or all going down. So that's why we know that we have a local maximum or minimum. The discriminant being positive, the same behavior everywhere, and then look at that second derivative, the second partial with respect to x, to determine the maximum or minimum. So this is your test, and we'll use this to classify the critical points when we find them. Okay, so now let's use the second derivative test to classify the critical points of this function. First, find the critical points. And we'll do that by finding where the partial derivatives are both 0. The partial with respect to x will be 2x minus 4. That partial will be 0 when x is equal to 2. We also need that the partial derivative with respect to y is 0. The partial with respect to y is 4y plus 4. That will be 0 when y is negative 1. So for both of these partial derivatives to be 0, x must be 2 and y must be negative 1. So we have one critical point. Okay, now I want to find that discriminant. Remember the discriminant, d, is the partial with respect to x, the second partial with respect to x, times the second partial with respect to y, minus the partial with respect to x, and then y squared. So let's find those partial derivatives. F sub xx is just the derivative of the partial derivative with respect to x. The derivative with respect to x again would be 2. F sub yy would be the partial of f sub y with respect to y, which would be 4. And now f sub xy is the partial with respect to x first, and then take that with respect to y, which will be 0. So that discriminant then really doesn't matter which point, we'll have 2 times 4 minus 0 squared. The discriminant is always 8. So it doesn't depend on what the point is. So the discriminant for this point is 8 also. Okay, so now when the discriminant was positive, we needed to look at the second partial with respect to x at that point. Well, the second partial with respect to x is 2, and it doesn't matter what the point is. So when the discriminant was positive and the second partial with respect to x is positive, that means we have concavity upward, which means that we have a local minimum. And the local minimum occurs at 2, negative 1. And if you actually want the local minimum, which is the lowest value, you would find f of 2, negative 1 to be 4 plus 2 minus 8 minus 4 plus 6, which is just 0. So the local minimum is 0. At the point 2, negative 1. Okay, now let's use the second derivative test to classify the points here. Now we already found the critical points of this problem previously. So we got critical points 0, 0, and 2, 0. 0, negative 3, and 2, negative 3. And then 1, negative 3 halves. So next let's find the discriminant for each of those points. Well, the discriminant, let's go ahead and get our partial derivatives again. We had our partial with respect to x was 2y, x minus 1, y plus 3. The partial with respect to y was x, x minus 2, and 2y plus 3. So now we need to find the second partial with respect to x, which means take the derivative of this with respect to x again. Well, the only place the x occurs is in this one term, so the 2y and y plus 3 are constants, and then the derivative of x minus 1 would be 1. The second partial with respect to y will be the derivative of this one with respect to y again, but y only occurs in one spot. So the x times x minus 2 are constants, and the derivative of the 2y plus 3 would just be 2. And now let's find the partial of f with respect to x first, and then with respect to y. So take the partial with respect to y of this first one. So we would have y in two places, so we need the product rule, but x minus 1 is our constant. 2y times the derivative of y plus 3 plus y plus 3 times the derivative of 2y. So we'll have x minus 1 times, let's see, 2y plus 2y plus 6, so we'll have 4y plus 6. Now, if you want to check yourself, remember f sub xy should be the same as f sub yx, since these partial derivatives are both continuous. So, okay, I'm just going to assume that we've got all these right. And now the discriminant is the partial with respect to x, the second partial with respect to x. So it's 2y, y plus 3 times the second partial with respect to y. So that would be 2 times x minus 2, and then minus x minus 1, 4y plus 6 squared. So I'm just forming the discriminant. By taking this times this minus this squared. Okay, so now the value of the discriminant for each of these points, plug in 0, 0. Let's see, the first term will be 0. We're going to get negative 6 squared. So the negative's outside. Negative 6 squared will be 36, but we have the negative here in the middle, so it'll be a negative 36. At 2, 0, you'll also get a negative 36. At 0, negative 3, you'll get a negative 36. At 2, negative 3, you'll get a negative 36. And at 1, negative 3/2, you'll come up with a 9. Now, once you determine that discriminant, if it's positive, then we'll have a maximum or minimum depending on the sign of f, the second derivative of f. So we'll next need to determine that. Okay, now at the point 0, 0, I'm just evaluating this function at the point 0, 0 would be 0. At 2, 0, with the y is 0, it's going to be 0 again. At 0, negative 3, it will be 0 again. At 2, negative 3, it will be 0 again, because now the y value is making this one 0. And the last one, at 1, negative 3/2, the f sub xx comes out to be negative 9/2. So now let's classify. When D was negative, we had saddle points. So that's a saddle point. This one's a saddle point. So as long as the D was negative, we have saddle points. And now we have a positive D here with the second partial derivative of x being negative, which means concave downward, which means we've got a local maximum. At the point 1, negative 3/2, and the local maximum is actually whatever the z value is, so it would be whatever f of 1, negative 3/2 is. Okay, now let's look at the picture on the next slide. Okay, so we have these 4 points here or saddle points. They're not real easy to see on the curve or the surface there, but you'll see that there are some places where the curve is flipping upward here and places where it's going downward, like here. So at each of those 4 points, there's points around that point that are higher and lower. Now, the way this is shown in the level curves is you see intersecting points. Now, another thing that we see is right here in the middle, we actually see a local maximum. And remember, when you have level curves that have concentric circles or curves around that common point, that's when you're going to have a high and a low point. So saddle points at those 4 borders, and then the local maximum on the inside.